Be seated, be seated. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I welcome you all to the public defense of the doctoral thesis of Ms. Jolien Malfait, which can be considered as the last step to become a doctor in science. My name is Professor Koen van der Abele, and I will be chairing this session. My first task is to officially and formally open this session. But before I do so, let me please ask you to switch off your mobile phones. And with that done, I can officially open this session. Jolien Malfait has presented to the faculty her PhD thesis on the topic Simulating the Impact of Wind Companion Interactions on the 3D Morphology of AGB Outflows, in partial fulfillment of the requirements for obtaining the degree of Doctor in Science, Astronomy and Astrophysics. The thesis work and the manuscript has been subject to an intense evaluation with in-depth questions and lively discussions with the members of the examination jury during a closed session on July 4th of this year. As a conclusion of this meeting, the jury members unanimously approved the work and admitted the candidate to the public defense. Before giving the floor to Ms. Jolien Malfait, I would like to introduce you to the members of the examination committee. As this is a joint undertaking between the two universities of KU Leuven and the University Libre de Belgique, de Bruxelles, there are multiple supervisors. Professor Dr. Leen de Sin, KU Leuven, Department of Physics and Astronomy, Institute of Astronomy. Frederik de Keuster, Dr. Frederik de Keuster from KU Leuven, Department of Physics and Astronomy, Unit of Semiconductor Physics. And the third supervisor is Professor Dr. Lionel Cies from Université Libre de Bruxelles, Institute of Astronomy and Astrophysics. The work has been evaluated by 5 jury members. Unfortunately, the 2 international jury members were excused for today's meeting due to the distance and personal conflicts in agenda. And they are Professor Dr. Daniel Price from Monash University in Australia and Dr. Jan Bolte from Kiel University in Germany. The local jury members are Professor Dr. Alain Jurissen from Université Libre de Bruxelles, Institut d'Astronomie et d'Astrophysique, Professor Dr. Jasmina Madelenic from KU Leuven, Department of Mathematics, Unit of Plasma Astrophysics, and Professor Dr. Hugh Sana from KU Leuven, Department of Physics and Astronomy, the Institute of Astronomy. Also, Professor Dr. Hugh Sana is excused for today's session because of stomach flu. As mentioned, I will be the chair for today's defense. My name is Koen van den Abele. I'm professor at the Department of Physics and Astronomy and chairman of the group of Science, Engineering and Technology at KULAK, which is the campus where it all began for Jolien. Ms. Jolien Malfait shall now publicly defend her PhD thesis. Jolien, you're invited to give a presentation of about 45 minutes about your research that you performed in the last 4 years. Afterwards, the examination committee will ask questions and discuss your work with you. As this is a public defense, I will also allow the public to ask relevant questions. I now give the floor to Jolien for her presentation.
Okay, thank you for the introduction, and thank you all for coming. Thank you for taking the time and doing the efforts to come to listen to me and join me on my public defense. In return, I will also do an effort to make this presentation as pleasant as possible for all of you, which means I will try to explain everything really well. So let's see. Because now the title that is there on top is Simulating the Impacts of Wind Companion Interactions on the 3D Morphology of AGB Outflows. And I'm afraid that for some of you that doesn't say much. So I hope that by the end of this presentation, you will understand what I mean with this. So I'll start from the very basic and introduce again what a star is, just to make sure we're all on the same level. Well, a star is basically a ball of hot gas. This star is also really bright in the night sky, which means that it's luminous. So it has a source of energy that is produced as light. This source of energy is inside the star, in the core of the star, and is basically in the main lifetime of the star, nuclear fusion, which means that two hydrogen nuclei are fused together into a helium nuclei, and this results in the production of energy. And this energy is from the famous formula of E is mc squared. You don't have to know the details, just that you know a bit where it comes from. And then finally, during the main lifetime of a star, the star is a nice and stable ball, which means that the radius of the star is also not moving that much. It stays basically the same during the first part of its life. And that is because there is a force inward, which is the gravity, which keeps everything nicely together. But if there would only be gravity, then everything would just collapse. So there's also an outward directed force, which is a pressure. And because these forces are nicely balanced, you have this nice spherical ball of gas that is a star. Now, one of the main distinguishments that we often make in stars is a distinction based on their mass. And this is so we have massive stars and low mass stars. And massive stars are all the stars that have a mass, an initial mass, above about 8 solar masses. So these stars are at least 8 times as heavy as our own sun. Then the other stars, which have a mass similar to the sun or up to 8 times the mass of the sun, are called low mass stars. These stars evolve in a different way. In my thesis, I'm focusing on these low mass stars, so I won't go into too much detail about these massive stars, but just to give you an idea, by the end of their life, these stars will explode as a supernovae. And then there's 2 options for what will remain after the supernovae. One is a neutron star, which is a rather small remnant and is rotating really fast. And the other option, if the star was really supermassive when it was born, with a mass higher than 20 times the mass of the sun, it will end as a black hole. And in this case, that is because gravity just overwhelms everything. Everything falls back to the center with a speed even higher than the speed of light. And that is why this is a black hole, because we cannot see inside it. But I won't go into more detail about this because we care about low mass stars. At the end of their life, low mass stars will start to expand. So they become much, much bigger. They also cool down because of this, and that is why we call these stars red giants. the red color indicates that it's a bit cooler. The blue color of these massive stars indicates that they are really hot. The stars are called giants because they are really giant. Here you see a not-to-scale image of the sun and the distance to the Earth, and you can see that this red giant will probably swallow the Earth at this stage of its life. Now, partially because they are so big, the particles in the outer layer are not attracted to the core of the star that much. The gravity is a bit less strong because they are so far away. And this helps to let this material escape from the star. And that is one of the reasons why in this stellar phase, the stars have a stellar wind, and they basically blow away their outer layers into the interstellar medium. So they enrich the interstellar medium with all this material that was once part of the star. Then after this phase, all this material that is being sent out into space will light up and be visible, if you observe it with a telescope, as a planetary nebula. And these planetary nebulae are known to have really complex structured, beautiful morphologies, as the one example that you see here. Then in the end, what remains of this star is a white dwarf, which is basically the remnant of the core of the star, which is a dead but still hot remnant. This is rather small because it's more planet-sized than star-sized, and all it can do is cool down and just end its life. Now, in my thesis, I mainly focus on these phases, which means the red giant phase with the stellar wind, and the link to these beautifully complex structured planetary nebulae. Okay. In the title, I said AGB stars. All you have to know is that AGB stars are these red giant stars. So I'll just go over the highlights again that you know what AGB stars are. So they are evolved low-mass stars. They are super big with a radius of about 1 astronomical unit, which is the distance from the sun to the Earth. And they have a strong stellar wind, so they blow away this material into the interstellar medium. This wind has velocities of about 5 to 20 kilometers per second, so quite fast, but not that fast in stellar terms. And they lose a lot of material, namely about 10 to the minus 4 to 10 to the minus 8 times the mass of the sun per year. So all this material gets blown into space. These winds are also one of the reasons why these stars are so interesting and so important to study, because by bringing all this material into the interstellar medium, they also impact and enrich this interstellar medium with a lot of dust and gas. And then we care about this because that is also the material from which new stars are formed. So one of the reasons why we want to study and understand these stellar winds. But now let's go back to these complex structured morphologies of this planetary nebula. Because in the simple image that I've drawn here, you see a star is nice and spherical and round, and then we have a wind starting from the radius of this round star. So basically, we don't expect any structures to form, we just expect a rather spherically symmetric wind. But then we see that in the next phase, we have these complex structures. So why do these structures arise? That is something that I'm interested in and that we want to study. Then we thought, if we want to understand this, maybe let's take a better look at these AGB stars, these red giants again, and their stellar winds, to see if they are actually spherically symmetric or not. And that is something that was done with the Atomium program, with the ALMA telescope. This is a super huge telescope in Chile that basically consists of a lot of different small telescopes that work together as one big telescope. And because of this huge telescope, we can resolve smaller scale structures in the winds of these stars. And that is what you see here. So what you see here are all red giants and their outflow. So the star is just in the center of the image, and everything around it is the outflow. And then the colors are indicated there. So everything that is colored red is moving away from you. Everything that is colored blue is coming towards you. So you see that these outflows are not nicely spherically symmetric. There's a lot of structures present here. For example, in this star, Achille, which you have seen on the first slide already, there's a lot of complex structures. There's some arc-like structures, some shell-like structures, and material going away from you, coming towards you, all mixed up. So this is not just a spherically symmetric outflow. Another example here is Hydra. Here you see that at one side, material is coming towards you, at one side it's going away from you, so you have this type of bipolar shaped outflow. Now, if we look at these structures and we put this planetary nebula next to it, we see that this already resembles this outflow much better than if you just assume a spherical symmetry. And this indicates that perhaps the mechanism that is shaping this complex planetary nebula is already present in the AGB outflow. So we can study the AGB phase to study what is also happening later in this planetary nebula. So what could be the origin of these complexities? This is maybe the most difficult slide, so I'll just go over it really slowly. So on the one axis here, you have the stellar mass. So to the left are stars that are rather small, not massive. On the right, you have the really massive stars. And here you have the stars that are similar to the sun. On the other axis, you have the percentage of these stars that has minimum one companion star, so a second star that is close to it. Then what else do we see? We also see different colors. These colors are linked to the temperature of the star. So massive stars are hot and blue, and low mass stars are rather red and rather cold. Then the crosses indicate the data points that we have, but in astronomy, you always have uncertainties on the data points because stars are far away, they're difficult to study, so you can see that is indicated here. So what can we learn from this graph? If we look at a solar mass star, so a stellar mass of 1 M-sun, 1 solar mass, and you go up to the data points and you go to the left, you see that about 50% of these stars has minimum one companion star. So the sun is alone, we don't have a companion star next to the sun, but half of the stars that are similar to the sun have at least one companion that is next to it. So this is something that we should take into account when we are studying the stars, because if you go to higher masses, you see that this percentage also goes up. So basically all of the really massive stars even always have a companion and never alone. So this is something that we thought, let's study this. So what does it mean if you have a companion? Here you see the red giant star. And if you add a companion star, then this means that similar to as the planets orbit around the sun, these stars will also orbit around each other and around their common center of mass, which is indicated here. So this basically goes like this. They are orbiting around their common center of mass. And these stars will also interact with each other. And if you have a stellar wind from this star, this wind can also interact with this companion. So that is what I mainly studied in my PhD thesis. So now you know the basic setting of this. From now on, I will often show similar things, but then in simulations. And you can look at this type of setup in different ways. You can look at it from the top, from above. If this is the case, I will put on my slide that we are looking at on its face on. If you're looking from it from the side or from the edge, we're looking at the system edge on. So in the next slides, this will be indicated so you know in which way we are looking at the system. So to study this, I use three-dimensional hydrodynamic simulations. This is a really basic way of what these simulations are. You have two stars. These are in the simulations as well, just like spherical dots. We don't model the stars inside or anything to keep it simple enough. And then we launch a wind from around this AGB star on spherical shells. So it goes a bit like this. And the stars are also moving around each other. So this is really simply said what the simulations actually do. So now let's take a look at one of my real simulations. So this is a 1.5 solar mass AGB star in the center, the big black dot. And there is a solar mass companion, so second star, at a separation of 6 astronomical units, so 6 times the distance from the sun to the Earth, and the stars are orbiting around each other. We are looking at the system face on, so we see the stars orbiting around each other. We don't look at the projection from above, but we look at a really thin slice in the orbital plane. So this is just the material in one thin slice. And what you see is the density, which means that if the color is really light, there's a lot of material. If the color is rather dark, there's less material. Okay, so what do we see here? We see that there is a spiral structure originating behind the companion. So the second star is orbiting. There's a two-edged spiral structure forming behind it. There's 2 reasons why this spiral structure originates. One is that the companion can gravitationally attract wind particles around it. So because it's attracting particles and it's moving, you have this spiral structure behind it. This is a bit similar if you would have a duck in a lake and the duck is also going around, then you can also expect that a spiral would just result. Secondly, you also have the movement of the HB star. So you have your HB star, it's launching a wind, but then the HB star is also doing like this, making circles, and this also creates this spiral-like structure. This is called the Coriolis force in physics. So what we see is that in the most basic case, we get a nice spiral structure in our simulations. And then, really nice for us, there's also some observations that show almost exactly the same. So in this example, you can also see that around the star, there's this spiral-like structure formed that can be observed in the wind. So this was a really clear indication that there was a companion hiding in these winds and shaping this spiral structure. But if we go back to these atomic observations, we see that we're not done yet. There's more complex things happening here. They're not just all nice spiral-like structures. So we need to think a bit further. Now, one thing that can change all these morphologies is the properties of the wind and the stars. So what I mean with this is that if the wind velocity is different, we will also expect different morphologies and structures to arise in the wind. The same goes for the orbital separation, which is the distance between the 2 stars, the masses of the stars, and the shape of the orbit. So we can make different simulations in which we change all these parameters to see if we get different structures except for the nice spirals. Secondly, there's also additional complexities. An AGB star is a rather complicated thing. It's not just a nice ball of gas, sadly. One of the things that it does is radially pulsating. So the radius really goes a bit like that, but then it's even more complex because it's not nicely like that. There's also asymmetrical stuff and clumps going on in the wind. And there's more of those things. And we cannot include all of these things in our simulations because the simulations that we have are already really computationally expensive. So we have to be careful because observations and simulations will never exactly match. So we can make simulations to understand what is going on, but we always have to keep in mind that we will never be able to match the observations exactly. What I did in my thesis is basically mainly the first point. So I make different simulations and study what happens if we change these properties of the wind and the stars. Okay, so now we go to the simulations. The simulation that you see here is the one that you saw before with a nice spiral structure forming around the companion. This simulation has a wind velocity of about 20 kilometers per second, which means it's rather fast wind. So the wind goes outwards quite fast. And on the other side, you see the same model, but with a lower wind velocity. So here the wind only goes outwards with a velocity of about 5 kilometers per second. And the consequence of this can you see by comparing these 2 simulations. Here you see that colors are rather bright. There's a lot of white in this region and bright yellow. And that is because as this wind is not going outwards very fast, material starts to accumulate in this inner region. So there's a lot of material there. And this also has an effect on the structure that forms directly around the companion. So here you have this nice 2-edged spiral structure, but here it's already a bit more complicated with a big wide region with a lot of material there closely around the companion. And then instead of this nice 2-edged spiral, you have this this spiral that originates already a bit in front of the companion, and this is what we call a bow shock. So if we zoom out a bit, you see that, I hope you see, it's not the best view on this screen, but both these simulations have a nice spherical-like structure. But then we were looking at this face-on. If we rotate our view, so we were looking at it from the top, now we can look at it from the sides. If you rotate our view, this looks like this. So instead of seeing the stars orbit like this, you see them going in front and behind each other. So this is a different view. And these are the same models that have these spirals. So now we see the spirals edge on. So we see the cross-section of the spirals. We see how high they are. This is the high wind velocity, low wind velocity model. And you can already see that it looks quite different. Yeah, so it's not the best colors that you see, but here you see that the structures are rather high. They come from here to there, for example, and they are a bit shaped like bananas. And the other one, you can see the big difference between these two is that the global shape and also the shape of the structure itself is a bit more elongated. It's a bit stretched out in this direction. And that has to do with this lower velocity. So this effect of this stretching, this flattening, is present in all simulations, and that is due to the movement of the AGB star and the companion around the center of mass. Because if something is turning, if you are on something that turns, you will always feel a force to the outwards direction. So there is a force in this direction, in the orbital plane direction. And because of this additional force, your morphology gets a bit flattened. And then this effect is just more visible in this low velocity model, just because the wind is more prone to this additional force. So this force has a stronger effect if the wind is slow. So maybe this helps to see the banana shapes a bit. And here you have elongated rings. So you see that there is a big difference. Okay, then another thing I said is that the shape of the orbit can also change. The previous simulations were always in a circular orbit, and then we say that the eccentricity is 0, but we can also have elliptical orbits, and then we say these are eccentric orbits. So on these orbits, they move a bit like this. And because the shape of this orbit is different, there's also a lot of complexities that are added compared to the circular orbit. So, for example, in the location where the stars are now, they are furthest away from each other that they can be on their orbits. This is what we call the apastron passage. But if they go half an orbit further, so the yellow one goes from there to there, then the stars are located closest to each other, and this is periastron passage. So throughout these orbits, the orbital separation between the two stars will change, will grow and will decrease again. And similarly, the orbital velocity of the stars will also change. So when they are at periastron passage, close to each other, the stars go really fast on their orbits. When they are at apastron passage, far away from each other, they go rather slowly. You will see this in the simulation. And these phase dependencies of this orbital velocity and the orbital separation also introduce a lot of complexities in the way the companion interacts with the wind. So let's take a look at that. Here you see again the high wind velocity model in the circular orbit with a nice two-edged spiral. And on the other side, you see the same model, but with an orbital eccentricity. So let's take a look. The companion passes at this side really quickly. This is periastron side. On the other side, it takes a longer time. This is apastron side, where they are further away from each other. And because of all these asymmetrical things, the orbit is asymmetric, you also get an asymmetrically shaped outflow. So the structure that is forming behind the companion at this side is different than at this side. Here you have a nicely two-edged spiral structure, and here things are much more complicated. And this is what causes this asymmetric global morphology. So here you have an Archimedes-like spiral structure. Here things are asymmetrical due to this eccentricity. So basically, you see that at this site, structures are a bit overlapping each other. They go faster outward, and things get a bit fake. While on the other side, you have spirals catching up on each other with a low density gap here. And that is because of the different way the companion interacts with the companion interacts with winds at each of these sites. Now we can look at the same models edge-on again. So we turn our view with 90 degrees. The left one was the one with the banana shapes. And the right one is these asymmetric eccentric orbits. So here, the banana shapes again. Here you see, similarly to the face-on view, that you have overlapping structures on one side and a low density gap here on the other side. Okay, then we can look back again at the model with a low wind velocity. So in general, we know that if the wind velocity is low, more material accumulates in the inner region, and this will always complicate stuff because the companion can interact with much more particles or material in the wind. So here you see the nice Archimedes-like spiral structure with the bow shock, and on the other side you see the same model but in eccentric orbits. And I won't explain these structures in detail, but what you see is that they are rather complex. They don't resemble an Archimedes spiral anymore. There's different type of structures at each side, so we get really complex morphologies if we have a low wind velocity and an eccentricity. If we zoom out, you see the Archimedes-like spiral, but it's not the best to see. But here you get something that doesn't look like a spiral anymore. It's a different shape. But I don't know if you can see it, but the shape recurs. So here you have the outer shape, then you have the second one. So at each orbital period, the same shape originates, and in this way you have this self-similar morphology. So it's one shape that occurs every orbit. Okay, this is if we look at the same models edge-on again. At the one side, you have these rather symmetric elongated rings. So both sides are a bit the same, and you have elongated rings. And here, if we draw something on all the structures, they look a bit like this. So they are more complex and clearly asymmetric due to this eccentricity. Okay, if we then zoom in on the stars, so we look closer at the stars, you get this. So what you see is the AGB star and the companion star. And you see that a lot of material is accumulating around this companion star because the density is really high, it's white, so a lot of material is there, and it's gathering in a sort of circular shape around the companion. And spoiler alert, this is what we call accretion disks. So all the material is gathering in a disk around the companion. Now, if we zoom in even a bit more, this doesn't look too good. Okay, the image is gone. Wait, let me just check if I can fix this. That you see the accretion disk. You see my screen? Okay. I'll just show it here and then I'll go back to the slides. So what you see here is the face-on view of this disk. Over the density, I plotted velocity vectors. And if you have good eyes, you can see that there's velocity vectors going around the companion. So material is orbiting around the companion star. And it's also spiraling in towards the companion. So this is why we call this an accretion disk, because it gathers material and material spirals in to the companion, and then the companion can gather this material and become a little bit more massive by gaining this wind material. If we change our view and we look at this edge-on, so if we look at this disk from this side, you see this. If you look at it from this side, you see this. We see that the disk has flaring it's a flaring disk. So if you look at it edge-on, and there's also something typical for disks in astronomy. Okay, let's go back to the slides. I'll have to cut it out. Okay. Now we understand relatively well what happens in binary systems. So AGB stars with one companion. So we thought, let's add something to it. Let's look at triple systems. Here you see the binary system, so the red giant with the second star orbiting around it, they're orbiting around their common center of mass. But if we add an additional companion, this one here, further away from this one, so we have a stable system, they don't interact too much with each other, they behave nicely, which is what we want, then all these stars will also orbit around their common center of mass, so on these orbits. So this entire system will go this way, and this one will just go this way, a bit like this. So this complicates the orbital movement of our AGB star quite a lot. And this will also complicate the interaction of both companions with the wind, which is what we studied with our hydrodynamic simulations again. Did you enjoy this? So you can be a scientist and check what you see, and I'll tell you what you should see. Okay, I'll just start it again and give some explanation. Okay, so we have a 1.6 solar mass AGB star with a close companion that is relatively of low mass, and then there's an additional 1.2 solar mass companion. So in the center, you see these two close stars orbiting around each other and creating these spiral structures that you see here. So this Archimedes-like spiral structure that we saw before in the binary simulations. And then there's this additional triple companion that is on top of this inner spiral structure and is creating an additional spiral structure that you see here. Now, because this outer companion has to pass all these waves of this inner spiral, you get this wavy pattern on its outer spiral edge. And then the third thing that you maybe can see is that the Archimedes spiral that is originating from this binary is together with this binary also moving around this common center of mass, and this is also reshaping this entire Archimedes-like spiral structure a bit, so it's being a bit pushed forward. You can still see it here, and in this way, this spiral looks a bit more like a snail shell spiral pattern, so it's a bit pushed forward all the time by the movement of this binary around the common center of mass. Okay, so this was again the face-on view. If we rotate our view and look at it edge-on, you see again here the inner binary with the tertiary companion. And you see these inner structures that arise from the binary. And then you have these large structures that arise because of this additional tertiary companion. So these are the general things that we see in these triple systems. Okay, Herakile is a nice AGB star with a nice morphological structure in its outflow. It made it to the cover of my thesis, so I had to talk about it. I have a bit of a love-hate relation with this star because it's really beautiful, but it's really complex and difficult. And Leen thought, let's give this to Jolien, she can do something with it. And I was like, so I tried to do something with it, but it's still a mystery to us, spoiler alert. But because it's so complex, we thought maybe it's a triple system. So in my paper on triple systems, we also looked at Herakile in a bit more detail. This is a bit more technical, but this is basically what we get from this observation after data reduction and stuff. All these images are two-dimensional images, and everything that you see in one such image, which we call a channel map, is all the material that is going away from you or coming towards you with a certain velocity. So the velocity is indicated on the top. So we can look at this. Here we go through all these different channel maps, and this gives you a bit of an idea of what the star looks like in a 3D way. So you go through it a bit like this, through all these velocity channels. And I think you can agree with me that all these structures are rather complicated. It's not just a nice spiral structure. It's also not nice banana shapes or flattened arcs. But yeah, there's a lot of arc structures, some shell-like structures. And it's also really difficult in this way because we don't have we don't have all the particles, we only have these certain channel maps, these certain velocities, and that also can make it hard to know, for example, if this structure, if this is the same one as this structure or not, so it's difficult to disentangle all these things and understand what this star actually looks like and what might be shaping it. But then, thanks to a radiative transfer code tool, Magritte, developed by Thomas Keulemans and Frederik Kuster here, we can also make such channel maps of our simulations. So here you see one of my triple simulations, but then represented in a similar way as it is here. And this we can use to, as far as we can, compare our simulations with the observations. So one thing you can see, for example, is that the velocities match quite well. So you have velocities up to about 9 kilometers per second in each direction, and this also matches with the simulation. Secondly, also the spatial extent of this simulation is rather similar to this observation. But then if we want to go into more detail and compare the structures itself, it's difficult to see the exact similarities. And we also have to be really careful if we want to say like, oh, this structure looks the same as that one, because as I said in the beginning, be careful when you compare observations to simulations, because it might also just be a coincidence that a structure is there and not there, or it's there in both simulations. So there's still some work to do if we really want to be able to say if R Achille is actually a triple or not. We can only conclude that it might be a triple. Okay, R Achille is this one, but we can also take a look at another star. This is W Achille. W Achille is the favorite star of my colleague, postdoc Thijsa Danilovic, who's in Melbourne, and I got to visit her, so that was nice. And I collaborated with her to study this star a bit better. So one thing she was seeing, this is one of the observations. Let's not go into too much detail, but what she basically saw was that there were some circular-like structures. So here they are just indicated by these lines, but she could distinguish that these structures were there. And then secondly, she has quite a lot of observations of W Achille, and W Achille is known to have a companion star. So the companion is there, it's known, but it's quite far from the AGB star. And then she also saw that the companion was moving almost directly towards the AGB star. And this was one of the indications, there were other indications, that this star is in an extremely elliptical orbit around the AGB star. So we worked together and I made some hydro simulations with the data I got from her to see if we get structures that look a bit like that, if we introduce this highly elliptical orbit that she thought the companion was on. I'll let you enjoy it again. So this is edge-on and face-on view. It's a really big orbit, so the companion is far away and is moving rather slow in this simulation, just because they're so huge. But you can already see it happen. You can see that here also these circular-like structures appear, and the same here. So she was right that probably there is a companion in a really eccentric orbit shaping these circular-like structures in the outflow. These circles basically originate because when the companion is coming really close to the AGB star, their movement is really fast, so the AGB star is also moving like this really fast, and this is what creates mainly this spherical structure together also with gravitational interaction of the companion. Okay, so these were a bit the highlights of the things that I did in my thesis. So to summarize, I made a lot of different hydro simulations, and we saw that a lot of different morphological structures can form if you vary all these different parameters. Then I also looked a little bit at observations, but they are super complicated, and there is still work to do to be able to compare these two exactly with each other, but we can already know now that if we just use these simulations to improve our knowledge of how these companions can shape the wind, that we can use this to work together with observational people to help each other out and unravel what is happening in these stars that we observe with ALMA. So I hope that now you understand a bit better what I mean when I say simulating the impact, so simulating impact of wind companion interactions, which is what you saw a lot, on the 3D morphology of these AGB outflows. And then I want to end by thanking all of you for listening. I hope I was able to make it a bit pleasant and understandable for everyone. And I want to thank my collaborators, because I couldn't have done all this work without them. So my supervisors and my close collaborators. Thank you also to the examination committee. And thank you to Ine for making the nice cover. And that was all that I wanted to say. So thank you very much.
Thank you, Ine, for this very nice presentations full of illustrations and relaxing music. We really appreciated that. We will now proceed to the question and answer session with the members of the examination committee. And as I mentioned earlier, the two external members of the jury, Professor Daniel Price and Professor Jan Bolte, they are excused for this meeting, but I can assure you that they have taken the opportunity to ask difficult questions and detailed questions during the preliminary defense in July. So that's checked. Also, one of the local jury members just this morning informed us that he was ill, and so Professor Hugues Sana will also not be present here and will not ask questions. So we immediately proceed to the two remaining local jury members that are present. And I would like to ask first Professor Dr. Alain Jorissen from Université Libre de Bruxelles, Institut d'Astronomie et d'Astrophysics, for asking questions. Please.
Jolien, I first want to congratulate you because the amount of work you did is really impressive.
Thank you.
And as a member of a jury for the thesis evaluation, it was really hard work to digest all that, which actually it was not really possible with so much material. So congratulations for that. And I think you opened new avenues, as you quite rightly said in your conclusion, bright avenues for comparing these simulations with observations. And that is probably going to give rise to many more theses in the future. I'll be rather brief in my question. I only have one, and because I spent some time to read your revised version of the what was it, the paper where you finish with the saying a bit more about observations as I and other jury members suggested during the private defense. So I was happy, of course, to read a bit about that. And I want just to make a brief comment on that. So I was interested by your comparison with the comparison of the properties of the accretion disk with observed properties. And you mentioned that you found in your simulations a pretty large temperature for the accretion disk of the order of 10,000 Kelvin, which will make this accretion disk appear in the ultraviolet. Whereas other observations, like I guess it was you were referring to ALMA or radio observations, or maybe infrared, I don't remember, would make this disk noticeable as well in the infrared. And I found that very interesting and challenging because it illustrates how much remains to be done with all this material. And so I guess that you will follow as well the committee advice to drop that material on some server to make it available to the community.
Yes.
So it was rather, it was more of a comment than a question. And,
yes, I can also not add that much to it. I agree that there's a lot of things we don't know because we see these hot temperatures, but we're not sure if the disks are actually that hot and how we can observe them. So basically, indeed, you're exactly right that there's still a lot to discover about these accretion disks. And I will indeed put the simulation somewhere on our website. I still have time to do that after in the next months.
Yeah, okay, congratulations. I will give the word to my neighbor.
Thank you.
Maybe I'll introduce you. Thank you very much, Professor Dr. Jorissen. Second jury member is Jasmina Majdalenic from KU Leuven, from the Department of Mathematics and the unit of Plasma Astrophysics. Please go ahead.
Thank you. So thanks again for a very nice presentation, and also I appreciate a lot this time what we discussed, that you have dashed lines which indicate different structures, because I study our closest star. I'm not a stellar physicist, but a solar one. So I maybe start with this beautiful picture which you have here. So all your simulations show the very circular structures when you see it, but the observations show this very nice wavy pattern, which looks like a snowflake almost. So what causes that wavy pattern?
Yeah, we're not sure. So there's still missing physics in our simulations. In observations, there's also noise, which can make things look more complicated. In my simulations, I've also always shown a slice through it, so the orbital plane, but I think I can show the I'll go here. So if you look at this, then you can see that it also looks already a bit more complicated when we look at these velocity channel maps. So that is one thing that makes, because this is just one example. Also, the spirals are always there. If you look at its face-on, edge-on, we also sometimes already had more complicated things. But I think, for example, in some cases, if we will include the pulsations of the AGB star, this can complicate things, as it will also interact with the structures around the companion. And yeah, because we see there are other groups in Sweden that study make simulations of this AGB star with these pulsations, but then they do not add the companion far away, so they focus on another region than we do. And they also have already a really clumpy, complicated winds. So we need to basically combine that with our simulations, and then you will get additional complexities. So that is one of the main things, I think, that we're still missing.
What would you need to combine these things?
Yeah, smart people that can implement the combination of them, and good supercomputers. We already have good supercomputers, but now the simulations already can take up to 3 weeks on such a good supercomputer. So if we have to model these different scales again, then that will add a lot of computation time, because you have to, resolve all these different regions, and that makes it complicated.
Okay, so this is what we have to work on, I guess.
Yeah, you can do that. Yes, but it's also difficult. So yeah.
And now you're already on this slide. This is 35. I have I wrote myself a small note. So you see that the observations show this very well-defined structure, while your modeling results are more smooth-like, and this is in most of the cases. So can you a little bit explain us why that happens?
Yeah, something that I added in this is, you can see it a little bit, maybe, that there's lines here.
Yes.
So I added these lines on top of this data, and that is why that helps really to see some structures more. So I did this to help us to see the structures better, but if you would remove that, it is also more smooth. So yeah,
this is the artistic impression, kind of.
Yeah, it's still scientific.
Okay.
Yeah.
And you talk about in your thesis about the gravitational slingshot effect. I am sure that most of the people here don't know what it is. Maybe you can explain us what is it.
Okay, so basically, so it has to do with that if the companion attracts particles, then there is, I can say this in Dutch, but let's think about it in English. you have angular momentum that is conserved. Yeah, and that creates that if a wind particle is going like this towards the companion, it can be slingshotted back in the other direction with a different velocity. So the companion is affecting the velocities of these wind particles. And that is why, if you have this two-edged spiral structure, these two edges have different velocities. So there's a velocity dispersion in the material behind the companion, and that is mostly there because of this gravitational slingshot and just how the companion is impacting these wind velocities of these particles.
Okay. Maybe 2 more questions.
Yeah.
So you said that the properties of wind and stars, which you have very much influenced modeling results. So how did you select them?
So the wind velocity, we know that there's a range in between 5 to 20 kilometers per second. So we just selected 5, 10, and 20 to have a good range. And then the eccentricity was also just going from 0 to keep it circular. Then in the first paper, we went to 0.25 and 0.5 to make it like higher and higher. And then we saw that it's basically enough for the next papers to just stick to this 0.5 and 0 because the in-between was quite logical in between them. But yeah, we just went a bit like selected parameters. Silke, who's sitting there, also had a paper that was a bit complementary to mine. So we selected different parameters and just made them range a bit to just see what their effect was on a really theoretical side, but taking a bit into account what would make sense according to observations.
Okay, and now the hardest question.
Oh no.
So if you would do your thesis again with the knowledge you have,
No.
what would you do different? And would you do something different?
Well, it's difficult because, I mean, I gained the knowledge now, so it's there. But I think, so for example, the first paper and the second paper are basically the same simulations, but we added H1 cooling a bit because what we saw in the first paper didn't make that much sense sometimes. So we thought maybe some cooling is missing. We have these hot regions. So if I already knew that we needed that, we could have just included that immediately and just skip the first paper, go to the second one, and I would have gained a lot of time that I could spend in looking at Herakili a bit more, maybe asking people to help me with it, because it's so complicated, and maybe I should have reached out to observational people earlier that could help me with it. So I think that's one of the main things. The final 2 papers were fine, so I would do them again.
Thank you very much.
Thank you for the questions.
Thank you very much for these questions also. So we proceed to the second group, actually. There are 3 supervisors for this work, and I would like to give the word first to the supervisor from Université Libre de Bruxelles, Professor Dr. Lionel Schiess.
Well, first, congratulations, Jolien.
Thank you.
Very nice presentation. Already asked you quite a few questions. Every time you sent me a paper, it was back full of comments read everywhere. And I was very glad to see that you could answer and even decipher my writing and follow the arrows so you can...
Mostly.
and you could answer. That was very good. So I have only a very few questions because, well, in all your talks, you discuss about 2 stars, but what if you put a planet instead of planetary companion instead of a star? Would you expect, well, the same morphologies? How would that change the picture?
Yeah, that is something that we've done. Maybe Silke has done it in her first paper. So a planet is, in our simulations, basically a really low mass star because we implement them in the same way. But a planet gives rise to, again, a nicely Archimedes-like spiral structure. But because it's so small in mass, the the density difference between the winds and the spiral structure is really low. So it's more difficult to see the structure. It's less pronounced, so it'll be difficult to observe it in some cases. But you also see a nice Archimedes spiral structure, and the 2 edges are also really close together. So it's just minimalistic spiral structure, but it's still there. If we put, in that example, it was a rather massive planet, a 10 Jupiter mass planet, and not too far away, but you can still see this nice spiral structure.
Yeah. Adding planets around the stars can also generate the well, not the turbulence, but the artifacts we can, well, not the artifacts, the structures we can see in the simulations.
Yeah, if you have, for example, stars, 2 stars, and you add a companion.
Planets,
yeah.
Who knows? You can make it very complicated. Also, a question is that, observations also tend to indicate that there are circumbinary disks, a disk that surrounds the binary system. I know that in our simulations, your simulation, could not really see it. Huh? How do you think we could get to that? Because we observe it, we know that it exists. What is missing?
Yeah, I think one of the main things, I think there's 2 things. I think we might have to add more cooling, maybe, in the general winds, because now, we have the good cooling around the companion star, which is why we get these nice accretion disks. But in the general wind, the temperature is not exactly right still, so we need to add other cooling mechanisms that are right there. And then secondly is that we need some radiative transfer things, so with what Mats has done, but I think we need to be able to model better that there's opacity, and then in that way maybe material can accumulate better into this disk. So I think that's the main things.
And well, a last question is about these accretion disks that you described in the end. We also see these accretion disks around, in post-AGB stars. Is there an evolutionary link between those 2?
We discussed this a bit. Probably. Yes, I'm not sure. We're not sure, I think, because in our simulations, the accretion disk consists of material that is from the wind, but in these post-AGB stars, you have these 2 stars and then a circumbinary disk, and their material is also being transferred from this outer disk towards the companion, and the accretion disk is made up mainly of that material. So it's different material that is making up the accretion disk, but it's consequent evolutionary phases, so probably there's still a remnant of this accretion disk of the AGB stars that survives up to the post-AGB phase, but we cannot be exactly sure. So it can also be that first, as the wind is fading out and the mass loss rate goes down, velocity up, that there's not enough wind material anymore, and that the accretion disk is simply being accreted onto the companion, and then a new accretion disk forms from the circumbinary disk. But we don't know exactly when and how the circumbinary disk is formed, so that makes it a bit complicated. If this disk is there already when the wind is still slow enough to make this accretion disk, then it can be just a nice transformation up to the post-AGB phase. But there's a lot of question marks when going from AGB to post-AGB, so that's why I think we're not sure.
More students.
Yeah.
Thank you, Jolien.
Thank you.
Thank you, Professor Sees, for suggesting future work. And there are also 2 supervisors from KU Leuven, and I would like to give the word first to Dr. Frederik de Keuster from the unit of semiconductor physics at the Department of Physics and Astronomy.
Hi, thank you. Also, first, many congratulations for all the hard work that you did.
Thank you.
We discussed a lot over the last couple of years. So perhaps let me ask a few questions for the audience also. You've shown all these beautiful simulations here, but what exactly is it that you're showing? How are these represented on the computer? And because you haven't mentioned the 3-letter word SPH, could you perhaps briefly try to explain for the general audience what it is and what it is that we are seeing here? That helps perhaps also to appreciate the complexity of everything that we see.
Okay, I'll just show a simulation again. Okay, I'll do my best. So as I said, the stars are not modeled in super high detail. They are what we call sinc particles, which means they are just particles that have a mass and in this way can gravitationally interact with each other and with the wind. But then this wind that you see here, it's a nicely smooth wind, but actually this is a smoothed particle hydrodynamics. So this wind consists of all particles that are then smoothed out to see this smooth view. So the wind is launched from the HB star, and there's like spherical things around the HB star that are distributed with a lot of particles with a certain mass that give this density. And then as these spheres go outwards, you get this wind that is originating. But then to make everything smooth, we have to interpolate everything. So if you want to know the density at a certain point, and it's not exactly the location of a particle, we have to use information of the surrounding particles to estimate what the density and other velocity and stuff would be at that point. So in this way, we smooth everything out by using all the surrounding particles. Is that sufficient?
That is sufficient. That also leads to a nice follow-up question. So you have many, many particles in your simulation then. And I guess the more particles you have, the higher resolution you get, and the better you can resolve all these features. But how do you know that you have enough particles in your simulation then?
So there's indeed a lot of particles in the simulation, and we can set the resolution to include more or less particles, but the number of particles is there's not a continuous distribution. We have to choose a certain amount of particles because you have to be able to be nicely distributed on a sphere, and it is only possible for a certain amount of particles. And then we can do resolution studies. So we can make the same simulation, but every time with a different resolution. So add more and more particles. And then we can compare those to see if they give the same results. Because if you add only like 100 particles or something, you will not get physically correct things. And when you add more and more, you will see that you get the same results. And then you know that there's going to be enough. I mean, you can also add more, but you also have to take into account the computation time, because if you just cannot compute it in more than a month, then yeah, it's not a good thing. So you have to take into account computation time and look if things are resolved in the way you want them. So for example, I showed you the accretion disk simulations. To resolve this accretion disk, we need a really high resolution, so that takes a lot of time to compute. So what we did is just cut out everything above, I think, 20 or 30 astronomical units. So we don't have to compute anything about these regions, because otherwise we cannot get this high enough resolution to resolve this disk. So we have to really think about our resolution and see that, like, depending on what we want to study, we choose different resolution and different boundary of which region we want to model. That's a bit related to if you want to include your AGB star that is pulsating, you have to focus on this inner region, and then it's really difficult to also compute everything around it up to the companion star. So you have to choose a bit what you want to resolve.
Okay, thank you. And then perhaps an annoying question, but you've shown a very nice picture of the ALMA telescope, and it's also perhaps a question for the audience, because I think for most people this probably doesn't really look like a telescope. Yes. Oh. So, and I know it's difficult to explain in general terms, but could you just make an attempt and say what it is that we see here and how we use it to observe stars?
So these are radio telescopes, which means it's not an optical telescope. So an optical telescope has mirrors and just increases the light you receive from a star, and then you can see it better. But in a radio telescope, we don't see the visible lights, but longer wavelengths. And because these wavelengths are longer, they're also more difficult to capture, and we need bigger telescopes. These are about, I think, 52, 56 telescopes that work together. Because if we want to resolve these fine-scale structures, we need a huge, huge telescope, and we cannot build it. We cannot build such a large telescope with one one telescope. So we need a lot of telescopes that can work together. So you can just put them far away from each other, and then they can work together as one telescope. So at each telescope takes some data. But then, because you also have gaps in between the telescope, there's also some missing flux, but at least we can resolve small details. So you can also put the telescopes closer together to have less missing flux, because you have less data that is lost. But then it's more difficult to see the small-scale structures. So in our observations, we even then combine data that is taken with the large setup and with the small setup to increase our observations. Yeah. Is that sufficient?
Thank you. That was enough torture. Thank you.
Thanks.
Thank you. I'm sorry.
Okay, and then finally, the supervisor of this work, I will give the word to Professor Leen de Sin from the Institute of Astrophysics.
Hi, Jolien. Congratulations. Really, you have done a wonderful job, not only today, but also through these last 4 years.
Thank you.
I promised Koen to ask you a few questions, and I will do so. Since, you know, we always have been gathering together with all of these scientific questions, and I would like to proceed even today. So you have been showing us quite a few simulations, some of them with the eccentricity which is not equal to 0.
Mm-hmm.
Do you believe that HB stars, at least with their companions, can have an eccentricity which is not 0? And why do you think so?
Okay, so maybe to explain to the audience, that is a returning question in our field of study, because there are something that we call tidal forces that will tend to circularize the orbit. So basically it goes to minimal state of energy, which is a circular orbit. And because HB stars are large and stuff like that, you tend to circularize the orbit with the companion. But what we see is that in these post-AGB stars, which is face rightly behind the AGB, we see a lot of companions, and there we can resolve the orbit of these companions, and we see that many of them are in eccentric orbits. And this observational picture really does not match the theoretical picture that we have. So something is missing in the theory, because we have the proof of these post-AGB stars that there are these eccentric orbits. In this AGB phase, it's really difficult to find the companion, to see in which orbit it is, because it's hidden in the wind, and because AGB stars are complex things, other things also don't work. But we can use this post-AGB phase to see that probably these eccentric companions must already be there in the AGB phase or at the end of the AGB phase. But the exact mechanism that is counteracting this circularization is unknown. It can have something to do with the mass that is being transferred, because if you create mass, you can also create some sort of energy, and you can get this eccentric orbit again. But I mean, they must be there, because you see this W Achilles star that is an extremely elliptical orbit, which is maybe a bit a different thing again, because there's not so many pass-bys. But yeah, it's something I sadly cannot answer.
It's all fine, we can't do either.
Yeah.
So, and then continuing on, you know that we have been working also together with Mats, one of your very close collaborators, on that star Pi-1 crew. Yeah? And now we expect that potentially, or we are not yet sure, but that its companion might have a slightly higher mass than the primary star. Now, given that, what kind of an accretion disk would you speculate the star might have? And what might be, is its accretion rate and its disk?
So what was the last?
The accretion rate, how would that scale? For instance, you have shown, I think on slide 14, you have shown a simulation that was quite close to its parameters, with the exception of N2.
Okay.
Yeah, isn't it? Yeah, there you have an N2, the mass of the companion, which is slightly below that of the AGB star. Do the same simulation, but have, for instance, a 2 solar mass companion. What do you expect?
Yeah. So since I haven't done it, I'm not sure, of course, but in general, a increase in the mass of the companion will also make sure that it can accrete more particles toward it, just because its gravitational force is stronger. So then I would also expect that the accretion disk is more massive and then also a bit larger. And it can also create more material just because it's, again, the same reason, it attracts more particles towards this. But yeah, for the details, we would have to run the simulation. Also, if it's more massive than the AGB star, this also means that the orbit of the AGB star will be quite strong, which can also complicate stuff. And I never did a simulation with a larger, more massive companion, so I'm not sure. But we can set it up if you want.
Yes, please. Yeah, and then one last question, and I know that colleagues have touched on that already. Yeah? So we are quite successful when it comes into simulating the spirals. So the bottom part of this famous atomium postcard, we have so much challenges in all of the other ones.
Yeah.
Why? What do you think so? You know, there's an axis that you're missing there, I think, at least one.
An axis that we're missing.
Yeah, some physics, some whatever.
Yeah.
Some...
Yes, so again, the pulsations of the AGB star, because if you see in the models of Freytag that the winds are already so complicated just because of these pulsations and these clumps. So then the companion will also interact in a different way, because you see in the triple simulations, if we just model the outer binaries, so just the AGB star with one faraway companion, you get a really thin spiral structure. And if you add this binary structure below it, then this companion also interacts with all these spirals, and that results in a really different structure around this outer companion. So this spiral around this companion is impacted a lot by what is happening in the wind below. So that is caused by this binary companion. So if we add these clumps and these pulsations, we might also get quite different structures that arise around the companion, because it will again interact also with this non-spherically symmetric wind. So I think that will do a lot. And then, yeah, I think that's the main thing. You want to hear more?
I'm fine, Jolien. Thanks
You're
a lot.
fine. Okay.
Yes. Chairman, thank you.
Thank you very much. Since this is a public defense, I can also allow questions from the public. And so if you have an urgent question that you want to pose, please raise your hand and I'll come to you with the microphone. All right. You're making me difficult.
Hi, Jolien. Great talk. For W. Aquile, you had some work that showed the simulations had these circles that kind of came out as the winter periapsis.
Yeah.
And it seemed like the circles are quite concentric, but the observations showed that they were not so concentric. Can you explain where that non-concentricity is coming from?
Yeah. So in the simulations, they're also not exactly concentric. It's maybe a bit difficult to see. It depends where you put the center. If you put it at the location where the AGB star is at the moment, or if the center of mass. But because the circles originate around this periastron passage, they're also a bit more towards the periastron side, so one side, because at that time they're close together, and because of the direction of the movement of the AGB star, they are a little bit more towards one side. So that it was at least the non-exact concentric thing in the simulations was in the same way as you see it in the observations. So it probably makes sense, at least. But I think in the picture I show, I probably cannot go, okay, I know why it's confusing. So there's different type of structures. I should have come back to the picture first. So the white one and the black one are only a little bit off center, so you can maybe not see it. And the other ones are probably not caused by the companion. So these ones are dashed lines. She saw them as well, but we think indeed, because of this offset that we don't see as much in the simulation, they are probably caused by another mechanism, and we're not sure what. Could be pulsations or some pulses or something. But if we match it with so we make the simulations with the correct orbital periods, and then there's one spherical structure each orbital period, and then we match it up quite well with this black and this white one. So you're absolutely right. This offset is not there that much in the simulations, and it's probably another thing that is causing these structures. Well seen. Thank you.
Okay. There's one more question, same row.
Yeah, thanks for the nice presentation. Actually, on the same slide, in those panels, you said this blue and red structure
Yes.
is from bipolar outflow.
The Hydra is.
Yeah, that one. I wondered, how can you distinguish a bipolar outflow from something that rotates?
Yeah, so Pi1 Gru here is rotating. So it has these blue and red structures are spread out over the entire image, and you have this white band of material that is like fixed if you only look at velocity going towards you. So you can see that the entire thing is rotating like this. Whereas in Hydra, you just see these clear structures more or less, and there's like here you also have some bipolar-like things, but it's not spherical, and it's not just a thing that rotates like this. It's just two jet-like things that go each in one direction.
Yep, thank you.
Thank you.
Any more questions? It's your last chance to ask some questions. Otherwise, you have to keep your mouth shut after this session. No more questions? Okay, then I thank Jolien and also the audience for discussion here, and also the jury members, and we will now go deliberate about the result of today.
Thank you.
We'll be back in about 10-15 minutes, so don't go too far. Be seated. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science, astronomy, and astrophysics. Jolien Malfait has presented to the faculty her PhD thesis on the topic simulating the impact of wind companion interactions on the 3D morphology of AGB outflows, in partial fulfillment of the requirements for the PhD in science, astronomy, and astrophysics. And she has defended her thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of the University of Leuven, I confer upon Ms. Jolien Malfait the degree of Doctor in Science, Astronomy and Astrophysics. Just one more advice, Jolien. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALEA European Code of Conduct. Reliability, honesty, respect, and accountability. Many congratulations to you as a new doctor and also to your supervisors. I hereby close the session.
Ja, Wixen. Er is denk ik wel. Ik heb ook bijna zo.
Ik heb er ook gezegd. Okay, now that all administrative documents have been completed, I think it's up to the supervisor to close the session with some words towards the new PhD doctor.
Jolien, first of all, congratulations, not only from my side, but also from the other supervisors that are here close to me. And indeed, I was invited to give, let's say, some kind of a speech now after this PhD defense, which I really do with pleasure. And there are quite a few things that come to my mind. And the first thing for sure is I know quite a few people that belong to your family. I'm teaching, I'm teaching General Physics 1. Always this hand.
That's language.
I know at least 4 people in person with this last name. I'm sure there will be more here present today. But I would like to change that name today. It's not Malfait. Bien fait. Jolien, you have really done it very well, very well. And for each of these little words or each of these little symbols, I would like to say a few words. I would like to start with the B of bienvenue And for someone here in particular in this room, to be of bananas. That one person knows what I'm after. Welcome to all of you. I'm so happy to see so many people that are here around today and that have been the support of Jolien also today. Once you're here at this stage, at this place, and you see these people, so many people around you, you know that you're there in support of you and not in support of these jury members. We always feel, that the backside who is against us. And then I start with the last parts of your name, your new name, the A. We start a bit in a scientific way, these AGB stars, where you had these two famous ones, W and R, Aquile. You even dare to say today that your starting point of your PhD was quite, or maybe too challenging. But it has been just the fact that I have given you that challenging object that we went so deeply into the modeling. And that we really had to do our best and really go that new avenue of doing all of these models. And you have said it so often, too. The why is intriguing, intrigerend. We don't know what we see. You have heard this many questions today upon what can we already model? We can do a few things, but there are still so many physics that are lacking. And this is exactly what we are. Scientists who are not afraid of the lack of physics, of the lack of understanding, but scientists who would like to see the new things and go to these avenues. And you started with some models, but you ended with doing a lot of theoretical modeling. You got even from the person here in the jury, which has a most theoretical background, a question or observations. And actually, I think, these observations, we can trust at this moment more than we can do our models, but that's life. This is how we learn the new things. And then the last part of your new name, Jolien. I say this letter in Dutch. In Dutch, the I is innemend. Jolien, having you in your group, you have been the person who glues everyone together and is still doing that. You got a lot of experience in doing outreach talks and have gotten very positive feedback on that. We also could see that today. I think it's the first time I had a presentation with music involved. I know you love dancing a lot. You have been yourself always during each of the group meetings, during each of the other things. You have been and are still very enthusiastic. Whatever we tried, you are sometimes a bit hesitating, but you never shied away. And we have been discussing on that, how to learn not to shy away, which clothes to have on. Red is a perfect color. If you have to defend something, have red color. It shows that you can prove something. So we have even been talking on all of these small things, since I think it's important. As a scientist, and in particular as a female scientist, that we prove that we can stand here. And then this N, the N of novel, of new. Sometimes, Jolien, you have been a bit, when we started into something new, you say, can I do that? And then I say, yes, I think so. Maybe not in the direct supervision of me, but why not? We had many co-supervisors that could help you. And I hope that this has learned you also other things in life. Novel things can be anxious, but there are many people around you that have complementary expertise, and together we can make a new story. And the last one, well, unluckily, is farewell. We realize that you will not stay in academia. It's a pity. But luckily, you're still on board for the next roughly few months, since we would like to use, between quotes, your knowledge to have that knowledge transfer to some new people that we start in our group. Since knowing what Jolien knows today is very difficult. She thinks it's normal that you know that and that you know how to do the simulations and what is the physics behind. That's not true. But we hope that we can educate some people, and your supervisor, now you will be the supervisor, so that a he and a she, so a new postdoc and a new PhD student, can learn some of the things that you have been learning throughout. Thanks a lot.
Thank you.
And together with Frederic, we have a little present for you.
Thank you. Wat zei je? De uitleg. Moet ik het dan... I see nice sweets at least, so that's already good.
I will just say a few. It's been a pleasure working with you, Jolien. Under very specific, weird conditions, I would say, because we are not sharing the same office or meeting very often, but we're chatting almost every day on WhatsApp. And I really appreciated the way you work as a scientist. When I ask questions, you go to the point and always get these very nice answers. I mean, your writing in English is just perfect, much better than mine. It's just, you just answer the way it should be with, consideration. You look also around you, and when you don't know, you ask. So this is also something, scientists, we don't know everything. You have to have that wisdom in some sense. And it's a pity that you leave, and we could not meet more often. But at least we had some good times in Perugia, where we had a meeting. I want to wish you all the best for your future life, even if it's outside academia. But we'll keep meeting in the coming months, and I really enjoyed working with you. It was really a pleasure.
Thank you so much. Thank you. I'll also open it afterwards. Okay. Well, thank you so much for the nice words. I didn't prepare a nice speech, but I'm really thankful for all of the three of you. Were a really complementary team. I needed all of you in different ways, and I respect all of you a lot. I don't know if I should go into detail because I wrote acknowledgments, so you can read my acknowledgments as well. But yeah, I feel like I grew a lot during the entire PhD, but like you said already, I gained a lot of confidence. I really enjoyed all these outreach talks and going to these conferences, talking to a lot of nice people. And that's all thanks to you, because I got to do this PhD. And Lionel, you saved me on helping me so much on all these simulations. And indeed, you're a nice person to ask questions to. You always responded quickly, and I wasn't afraid to ask questions, which is also thanks to you. And yeah, you just all three were always there for me, which is super nice. And I'm really thankful for that. And then everyone here, everyone has been important, my friends, my family, and IBS is such a nice place to do a PhD. So I'm thankful to all of you. So thank you so much. I wrote a small card for all of you. Oops, sorry, to say thank you. And then I also bought some chocolates because I was like, what does everyone like? Chocolates. So thank you. So I hope you all like chocolates. I know you like chocolates. I know you like chocolates. That's a good thing. Like, just because she always has chocolates in her office, which is a really nice thing. Office, so. Yes, that's the only way I know she likes chocolates. Do you also like chocolates? Yeah, I like chocolate. Good. So thank you so much. It was a nice adventure. And I hope the reception is ready so you can all go upstairs here and enjoy a nice evening. Thank you so much.